So I'd like to tell you today about the connection between particle physics, which many of you are involved in, and cosmology, which a small group of us are involved in. And really this gets to the issue that we believe we can learn about fundamental physics, which is what we're all interested in, by observing particles that come from space. So before I begin, I want to tell you there are three ways of listening to this talk. The first way is of motivation. So some of you you're all working on different experiments here, and you've all been told how important these are experiments from the particle physics point of view. I want to give you a slightly different angle on them. Many of them are interesting from a cosmologist's point of view as well. So we'll give you a slightly different angle, a different reason to wake up in the morning. The second way to listen to the talk is many of you are second, third year undergrads, and you're beginning to think about what you want to do with your future. So I want to lay before you some of the exciting things that are going on in cosmology, and perhaps this will lead you to think that this is where you want to end up, where you want to do your work. And then I have to confess that if you're going to end up in our field as a physicist, one of the most popular ways of listening to talks is this way. So this is a third independent way of listening to this talk. Okay, so to begin with, I want to explain to you, really what I want to get at is that we're on the verge, or we have, of the last decade, uncovered physics beyond the standard model. In order to explain that, though, we first have to be on the same page when we talk about what the standard model of particle physics is. So it turns out it can fit on a t-shirt. Literally can fit on a t-shirt. There's a paper, this is a paper from Steven Weinberg about exactly 40 years ago, I guess, 1967. And this equation 4 here is the standard model of particle physics. So the standard model of particle physics is just one simple equation in a paper that appeared 40 years ago. Let me just extract out the important parts of this equation. The standard model says that there are basically just a handful of elementary particles. There are 4 particles, or bosons, which mediate the fundamental forces. The photon mediates the electromagnetic force, and these 3 other bosons, these are heavy, the W's and the Z, they mediate the weak force. So those are the 4 particles which mediate, the 4 bosons which mediate the forces. And these mediate the forces between that act on fermions, one of which is the electron, and the other of which is a massless neutrino. So if you look at this formula here, this has each of these 4 particles interacting with an electron and with a neutrino. And in addition, in order to give the electron and these 3 other guys mass, you need some kind of mystery particle called a Higgs particle. And that's the, 1, 2, 3, 4, 5, 6, 7. That's the 7th particle. And these particles constitute the basis for the standard model of particle physics. So since then, there have been 3 minor extensions to the standard model. And all of them, by the way, won a Nobel Prize. So the way Weinberg wrote down the model, you can barely see this. There was an electron, there was a neutrino associated with it, and there were 4 particles. There was a photon, a Z boson, and 2 W bosons. So there were 1, 2, 3, 4, 5, 6, and then there was a Higgs. Good, thank you. And then this will help you engage the talk the third way, with the sleeping way. So the first extension is that in addition to the leptons, the electron and its associated neutrino, it turns out that there are quarks as well. So associated with an electron-neutrino pair is an up-down quark pair. That's the first extension of the standard model. The second extension is that in addition to the electromagnetic force mediated by the photon and the weak force mediated by the Z and the W, there is a strong force mediated by gluons. And the strong force interacts only with the quarks, not with these guys at all. So that's the second minor extension of the standard model. It's pretty straightforward, actually, to just extend Weinberg's initial equation to include these 2 effects. And it's similarly straightforward to account for the third extension, which is that, you'll notice that this little block table here, there are not just 1 copy of these particles, but there are 3 separate generations or families or flavors of these copies. Each, let's call them flavors, okay? So let's call them generations. So each generation has a lepton pair, a charged lepton, in this case an electron and its associated neutrino. There's also a muon and its associated neutrino, a tau and its associated neutrino. And each one of those pairs, lepton pairs, comes with a quark pair. In this middle case, it's the charmed and the strange quark. In this heaviest case, it's the top and the bottom quark. So that's it. That's the standard model of particle physics. And if you couple that with a theory of gravity, which we have, Einstein gave it to us about 100 years ago, general relativity, you're basically done. You're able to explain all phenomena that we observe in the universe. In particular, what the Standard Model has enabled us to do, since it was first discovered 40 years ago, is to do cosmology. So we can actually use this basic framework and make predictions about what the universe looks like and how the universe evolved in time. So let me show you that here on a graph, which has on the x-axis the age of the universe. So we're down here today. The age of the universe is 14 billion years. And what I'm showing in this y-axis are the distances. So here I've kind of tried to indicate something, say a pair of galaxies, for example, that are separated by 10 billion light years. So imagine a pair of galaxies that are today separated by 10 billion light years. What this simple curve tells you is that if you put all those ingredients on the previous slide together, when you went backwards in time, the distance between those objects was smaller. So that, for example, when the universe was only about a minute old, they were separated by only 1 light year. And this curve denotes or represents what we call the expansion of the universe. Right? That's what the expansion of the universe means. It means that the distance between things is getting bigger. And so you've all heard of the expansion of the universe. That's exactly what this line is supposed to indicate. What the Standard Model is enables us to do is fill out this timeline. So we're able to go backwards in time, understand the distance between things was smaller, we're able to understand what was going on at various times. So for example, we can put different markers in these different epochs. So today we can measure the expansion rate of the universe, and I'll get to that a little bit later. When you went back, the universe was only 400,000 years old. Before then, the photons in the universe were talking to the electrons and the protons, and everything was tightly together in this whole epoch pre-400,000 years. But after then, the electrons and the protons combined to form neutral hydrogen, and the photons just traveled freely to us. So when we see the photons that comprise today what's called the cosmic microwave background, we're looking at a picture of the universe when it was only 400,000 years old. Quite remarkable, right? So this is clearly an important epoch. There's another important epoch when the universe was only a few minutes old. The light nuclei, the protons and neutrons, fused to form light nuclei such as helium and lithium. And we can test these predictions. We can predict how much helium there should be in the universe, how much deuterium, go out and make observations. And it turns out that those observations agree with the predictions that the light elements were fused when the universe was only a few minutes old. If you go back even further, you can go back to the time where the universe was not made up of protons and neutrons, but rather these separate quarks. Right? So this is the so-called quark-hadron phase transition. The universe was only a fraction of a second old. So if you were here 10 years ago, the whole talk would have been devoted to discussing these various things, which we've been able to do because we know the Standard Model. So in other words, cosmologists have borrowed from you physicists, from the physicists who taught us the Standard Model, and you've enabled us to do cosmology. And so now we're at the stage where we're going to return the favor to you. And we're going to give you something back. Let me show you how that goes. Okay? Yeah, my experience is that when this doesn't work, people end up clicking and ending up on page 30. So I'm trying to exhibit a little patience. In any event, it's clear that it's not just cosmology that the Standard Model explains, right? If you think about all the phenomena that have been explored at Fermilab and at all the largest accelerators in the world, every single one of them, every single bit of phenomenology that's been observed here at Fermilab or anywhere else can be explained within the context of the Standard Model. So the Standard Model explains not just cosmology, right? It explains all of particle physics, and it does it beautifully with just that very simple block structure we explained. If you think about it, though, it's not just particle physics, right? In the pyramid of knowledge, particle physics sits at the base, right? And on top of that are things like nuclear physics, and there's atomic physics, then there's solid state physics, and from that we learn about chemistry. Chemistry determines how biology works, and if you go upwards, biology really determines psychology, which determines how groups of people interact. And then, so if you know particle physics, you can predict the winner of the 2008 election. So in that sense, the Standard Model has been remarkably successful, right? In fact, if you think about it, this has been going on for some 40 years, and here's a little secret. You've probably heard some of this spiel one way or another since you arrived here. But actually, the secret is it's been a little bit too successful, right? So think about it. We have this theory that explains everything, right? So then what do? Right? What do we do next? Because we have a theory which explains everything. So what we really would like to figure out, we like to burst the theory. Really what science is it's knowledge at the edge, right? So it's great that we can explain so much, but what we want to do is burst the bubble. We want to go beyond the standard model, find physics beyond the standard model. So in that sense, the success of the standard model, the fact that the standard model can explain all phenomena is a failure also. It's a failure in our discovery. Except. So what I'd like to do in the remaining 45 minutes is describe to you several phenomena that we've observed, physics particles from space that we've detected, and these phenomena cannot be explained by the standard model of particle physics. So in order to explain them, you have to introduce new physics, new fundamental physics. So in that sense, it's not just being a cosmologist is cool. It's being a cosmologist, we're being useful finally. We're able to teach you, we're able to teach the particle physicists that there's something new that they did not have on Weinberg's t-shirt. So I'm going to go through this in a little bit of detail. Before I do, I want to ask if there's any questions about just make sure we're on the same page with this standard model stuff.
You're all sleeping.
Ah, you're doing mode 3. Okay. Good. Okay, so let's start. There are there are several phenomena, 4 actually, that cannot be explained within the context of the standard model. The first one is the following. Here's a picture of the sun, right? So many of you have seen the sun, right? But you've seen the sun in a different way. The way you've seen the sun is you've seen the photons from the sun travel through space and hit your eyes, right? That's the way you've seen it. This is a picture of the sun not taken with a camera which detects photons, but taken with a camera which detects neutrinos. So the sun is so hot that there are nuclear reactions going on in the center of the sun that emit neutrinos. Those neutrinos propagate to us, and we can actually take a picture of the sun in just neutrinos. So that's quite remarkable. What's more remarkable about it is that we've been able to quantitatively analyze these neutrinos, and we're able to make predictions for how many neutrinos we expect to see. That's these yellowish bars here. And there's a number of different experiments. The predictions are that the number of neutrinos we should see, turns out, is about a factor of 2 or 3 higher than the actual number of neutrinos that are observed. So what that means is there's some deficit of neutrinos. The sun is producing these neutrinos, and actually what the sun is producing are electron neutrinos. Remember, there are 3 types, 3 flavors of neutrinos. The sun is producing the electron type. And what's happening is, as they travel the vast distance from the sun to us, the neutrinos are transforming, changing flavor as they propagate over these large distances. So the neutrinos start out as electron neutrinos, but they don't show up in our detectors, which try to find electron neutrinos. Rather, they show up as some different type of neutrino, which our detectors can't see. So either a muon neutrino or a tau neutrino. So this phenomena of neutrinos changing flavor cannot be explained in the context of the standard model. And actually, many of you, how many of you are taking quantum mechanics courses now, or have taken them? Okay, so about half of you. I usually assume that most of you who taken one didn't raise your hand. So here's an example. Those of you who have taken quantum mechanics can actually analyze this. So here's what you want to do. You want to start out with a quantum state, which has electron neutrino, which is all electron neutrinos produced in the sun, and no muon neutrino. And the way you do it, see how that state evolves in time, is to evolve it with the Hamiltonian, right? Have you seen this equation? And then what you want to see is what that final state looks like at a much later time t. So if you look carefully at that t-shirt formula I showed you before, the Hamiltonian that Weinberg wrote down had no mixing term. There was no term which mixed the electron neutrino with the muon neutrino. So no matter how complicated this is, something starting as an electron neutrino would remain an electron neutrino. So the standard model of particle physics does not allow for these transformations. And in fact, the only way to get these transformations is if you add a mass term for the neutrinos to the Hamiltonian. And this constitutes the first evidence for physics beyond the standard model. So these transformations go hand in hand with the idea that neutrinos have mass. And in fact, the conversion rate from one type of neutrino to another depends on 2 things. It depends on the masses of the neutrinos, and it also depends on the extent to which they mix into one another. They can have masses and not mix into one another. So it depends essentially on 2 parameters. It's not that important to go into the details of these parameters, but there's one very interesting thing about this graph. And that is the colored lines here denote data that's taken from a detector that looked into space, right? It looked in for neutrinos that are produced in space, and what that detector decided was that the only way to account for these observations is to have transformations, which then lead to the fact that the mass of the neutrino has to be non-zero. So these contours cut off over here, which means that below here is ruled out, right? And below here means zero mass. Zero mass is down there somewhere. So this experiment from space, that looked at particles from space, decided that neutrinos had to have a mass. The thing that's very interesting about this is that the black contours here denote data that was collected by the Minos experiment here at Fermilab. And that's a different type of experiment because the neutrinos are actually produced by Fermilab itself. So this is an example where we had initial discovery of particles from space that's been confirmed in an accelerator-based experiment. Right, you see the data, the contours exactly overlap with these space contours. So it's a very nice complementarity between the space-based detection and the follow-up with the Minos experiment. And let me just mention that this interpretation, which seems to be correct, the neutrinos have a mass, has deepened a big mystery of particle physics. So here's something which you might have seen also. This is the mass of the particle. We like to think about masses in units of electron volts or giga-electron volts. The masses of those heavy bosons I talked about are about 100 GeV, or giga-electron volts. And the mass of the electron is about a half of an MeV, and the quark masses range somewhere in that range. So the range of masses range from over about 6 orders of magnitude, right? This is one of the big mysteries of particle physics. How do you get it so that you have a big range, a big disparity in the masses of the fundamental particles? Shouldn't they all be roughly the same size? Understanding that is something we haven't been able to figure out. If you add in the recent results from neutrinos, the mystery of mass deepens, because this is where the neutrino masses lie. So this mass disparity has gone from a 6 order of magnitude thing to a 16 order of magnitude thing. So you, as the future physicists, have a harder problem now to solve. Right, so this is the problem, trying to understand the disparity in the masses. Fortunately, we have a vibrant experimental path ahead of us, and many of these experiments that we have planned out are conducted here at Fermilab. There's the Minerva experiment, NOVA, SciBoon, MiniBoon, Minos. So there are 5 neutrino experiments here operating or planned at Fermilab that hope to get at this mystery of mass. Just a show of hands, how many of you are working on one of those 5 experiments? So about a half dozen of you. Great. Okay, good. So that's the first piece of evidence for physics beyond the standard model. Let me turn to the second piece of evidence. So here's a typical galaxy you might see in space. We can observe the stars in this galaxy. This is a galaxy far away from our own. We can observe many millions of billions of stars in individual galaxies. We can observe stars close to the center and stars very far away from the center of that galaxy. By using the spectra of these stars, we can measure how fast they're moving around the center of the galaxy. So we can make a plot like this. We can put on this, measure how far away the star is from the center of the galaxy. That's easy, just point the telescope. And we can take the spectrum of that star to measure how fast it's moving around the center. So this is called a rotation curve, the velocity versus the distance. You notice from this picture that most of the light, the starlight, is encompassed in this yellow band. So the vast majority of the billions of stars are in here. There's only really a handful out here. So if you translate that into what you expect is the mass is dominated over here, and therefore you should be able to apply Kepler's law, which many of you have probably learned, to determine what the velocity of the distant stars should be like, because most of the mass is concentrated in the center. And what should happen is that the velocities of these distant stars should fall off as 1 over the square root of the distance. So this is something which I think most of you have seen, right, in a class, that the Kepler's law tells you it should fall off as 1 over the square root of r. In fact, what we observe is not that. We observe is flat rotation curves. So the only way to understand that, or at least the easiest way to understand that, is to say that the stuff that's shining is not all the stuff that's there. There must be something that's not light, that's dark, there must be mass here that's dark, let's call it dark matter, that permeates this galaxy, and all galaxies for that matter, that's inducing these velocities to go from their Keplerian shape to the flat rotation curve shape. So this is perhaps the easiest and the oldest piece of evidence for what is called dark matter in the universe. So this is a pretty straight, so that's the first piece of evidence. Over the last decade or so, we've accumulated another piece of evidence, which is a little more complicated to explain, but it's pretty cool. So bear with me. And the take-home line is that this is a completely different piece of evidence for dark matter, right? Completely different. So the people who know about that don't know about this, and vice versa. Completely different things. So this is the argument. The take-home line is that the universe would be too smooth if there was no dark matter. And what do I mean by smooth? What's the density in this room, roughly speaking, in grams per cubic centimeter? Does anyone know? 42, exactly. So it's roughly 42 grams per cubic centimeter in this room. What's the density in an average place in the universe, roughly, in grams per cubic centimeter? Does anyone know? Not 0. Give me 10 to the minus whatever. Anyone?
10 to the minus 42.
Right, it's about 10 to the minus 29. So there is a vast range of densities, right? In this room, it's of order 1 or 10 or 100 grams per cubic centimeter. We are far from an average place in the universe, right? So the density in this room is way, way bigger than it is in an average place in the universe. So the question is, how did that happen? And that question is accentuated and made more difficult by this observation. So this is an observation of the universe when it was 400,000 years old. Remember I showed you that picture before? So these are photons that come to us when the universe was 400,000 years old. And this is what the universe looked like at that time. This picture tells you nothing except that there are some hot spots and some cold spots. It doesn't tell you the size of them. So let me tell you that this temperature here is equal to the temperature here to 1 part in about 10,000. Right? So basically, at that early time when the universe was just 400,000 years old, the universe was damn smooth. Right? Basically, there was the temperature was the same. That means the density was the same. There was the same number of protons here as there were here to 1 part in 10,000. So there was nothing like the disparity of 10 to the 42, whatever you want to say, that exists today back when the universe was much younger. So the question is, how did we get from this state, which was very, very homogeneous, to this state? This is an observation from the Sloan Digital Sky Survey, which shows that the universe today consists of lots of filaments and voids of filaments of galaxies, punctuated by large voids with basically nothing in them. So how did we get from this state where delta rho over rho, the fractional change in energy density was 1 part in 10,000, to this state where delta rho over rho was 10 to the 40, 10 to the 30, whatever. So that's the question. And the answer is we think we know the answer. That there are more people on this side of the room than there are on that side of the room, right? So over the course of 14 billion years, what's going to happen, if you stay seated for that long, is that gravity will attract the people on this side of the room. Due to gravity, it's an attractive force, right? So you guys will all migrate over to there. And so that's called gravitational instability. And we believe that the same thing operated here. These small, over-dense regions, even though they're very small, gradually accreted more and more matter around them as the universe aged, until eventually these vast and majestic structures arose. So that's the qualitative answer. Quantitatively, it doesn't quite work. So we can plug in the numbers. We can plug in the numbers. The distribution was smoothed to 1 part in 10,000 back there. General relativity predicts that the perturbations would have grown by a factor of 1,000 since then. So the delta rho over rho, the inhomogeneity would still be only about 10%. In other words, we would not be here, right? Because we're 30 orders of magnitude more dense than the average place in the universe. So there's a quantitative way of seeing that. And this is what we can plot something called the clumpiness. So once the clumpiness goes above 1, basically all hell breaks loose. The system goes nonlinear. So above 1 enables you to get to very high density. So the minimum requirement for a realistic theory is that the clumpiness factor has to go above 1. And I'm plotting this as a function of large structures and small structures. So on very small scales, like in this room, the universe is very, very clumpy. On larger scales, actually it's not clumpy at all. If you draw a circle around a very large region of the universe, and then draw another circle around a similar sized thing, a million miles away, you're going to get the same amount of stuff in it. Right? So it's only on small scales where things are clumpy, and this plot depicts that. This is the data. And what you see is a theory with no dark matter doesn't quite cut it. This is essentially what I showed you in the previous plot. That the inhomogeneities are at about the 10 to 1% level. So if you didn't have dark matter, you wouldn't be here. Right? So this is a quantitative way of expressing the fact that a no dark matter universe simply doesn't work. You have to have dark matter in order to understand the richness of structure in the universe. So the question is, if we have multiple, I've shared with you two pieces of evidence for dark matter, right? These galaxy rotation curves and the cosmological clumpiness argument. The question is, if there is dark matter, can it be made of stuff in the standard model? And the answer is no, it can't be. There is a list of, list of requirements that the dark matter has to satisfy, and no particle in the standard model satisfies these four criteria. So you have to go beyond the standard model, and that sounds exciting, and it turns out it's even more exciting than that, because about 30 years ago, after Weinberg's standard model was introduced, people came up with the idea of supersymmetry. Supersymmetry is a theoretical idea which posited there's a symmetry between the bosons in the universe and the fermions. So, for example, there's a symmetry between an electron, and it has a partner, a supersymmetric partner called the selectron. Every lepton has a supersymmetric partner called a slepton. Every quark, a supersymmetric partner called a squark. So there's an electron, a selectron, a top quark, and a stop squark or stop squark. There's a photon and a photino, a Z boson and a Zeno, a W boson and a Weno. Right? I'm not making this up. So that's the theoretical idea, and this was around for a long time. And eventually, about 20 years ago, someone realized that this edifice of supersymmetry is good not only for a variety of reasons that theoretical particle physicists were interested in, but also it naturally provided one of these heavy partners of the normal particles could be the dark matter. So the race is on to find supersymmetry and to find dark matter, and we have around the world now literally dozens of experiments engaged in this race. So, for example, here at the Tevatron, there's the possibility that we, over the next year or two, will find supersymmetry, which will point to these heavy supersymmetric partners as the dark matter. Actually next year, the LHC, the Large Hadron Collider, will begin operation in CERN, and that will be almost definitely discover supersymmetry or something like it. And in the future, we hope to bring to Fermilab the International Linear Collider, which will study very carefully the properties of these dark matter particles produced in the accelerator. So this is one whole line of addressing the dark matter issue in accelerators. There's another whole line, and that is, if you think about it, there's lots of dark matter in the universe today. So, for example, there's about one dark matter particle in my hand right now, and it's traveling at about 200 kilometers a second. So if I open my hand like this, there are about 10 million dark matter particles passing through it every second. Right? So if I was clever enough, I'd win a Nobel Prize if I could just feel one of them. But so that's the goal, really, to catch one of those dark matter particles. So one way to do it is what's called indirect detection. There's a host of experiments doing that, including the GLASS survey, which is going to launch at the end of this year. And what that is they look for dark matter particles in space. Two dark matter particles will come together and annihilate and produce huge amounts of radiation. So they look for that radiation. So there's a whole bunch of ways of doing that, and this is a whole line of thinking of finding the dark matter via indirect detection. There's a more direct way called direct detection, and what that is it looks for a dark matter particle coming through, coming towards us, and hitting a detector on Earth, or preferably underneath Earth to get rid of cosmic rays. And at Fermilab here, we're involved in two such experiments, the CDMS experiment and the COOP experiment. So this is a three-pronged approach which we think is likely to pay dividends within the next 5 years or so. We really think we're on the verge of detecting this new fundamental dark matter particle. And this would indeed be really a remarkable piece of evidence for physics beyond the standard model. Let me just, before going to the next thing, I'm just wondering, how many of you are working on either the Tevatron-related stuff or LHC via CMS, or either of these two dark matter experiments? How many of you are working on that? Oh, great. Okay. And I also mentioned the Sloan survey. How many of you are working on the Sloan survey? Oh, okay. So already we're up to more than half the group is working on cosmology experiments. You thought you came here to Fermilab for a particle physics experience. Really, you're all helping us out in cosmology. Okay, the third piece of evidence for physics beyond the standard model has to do with distant supernovae. So a supernova is an exploding star. Let me show you how they detect these things. So they take a telescope which scans the sky, or takes a large image of the sky, and it does it roughly, 1 week, and the next week, etc. and they compare images of, say, here's an image at time 0, here's the same image of the same part of the sky 3 weeks later, and you can notice a slight difference between this little thing here and that little thing there. So they take the difference between these two sets of pixels, and this is the difference between those two things. So clearly something's happened in these 3 weeks. They can attribute that to a supernova, and then they go and do a follow-up work with the Hubble Space Telescope and actually can see very accurately and take the properties of this distant supernova. So supernovae are tremendously important for 2 reasons. First of all, they are bright, so they can be seen from very far away, so that's important. That means, remember, we can see the sun, right? But we see the sun when? We don't see it as it is now, right? We see it as it was 8 minutes ago, right? Because the light takes 8 minutes to travel to us, right? And the center of our galaxy we see as it was 10,000 years ago or something, right? So the further away you're going, the further back in time you're going, right? So if we see these supernovae from very, very far away, we're actually seeing the universe not as it is today when it's 14 billion years old, but as it was when it was 1 billion years old, right? So the fact that they're bright is actually quite important. And the second aspect of them is that there are standard candles. What that means is roughly all of these supernovae have the same intrinsic brightness. So if we see them, there's this law, which you're probably in the process of learning, so you probably know better than I do. But there's a law that the flux you observe is equal to the luminosity of something, how intrinsically bright it is, divided by the distance squared, right? So if we know how intrinsically bright a supernova is, we can measure nearby ones to figure that out. Then the ones we see from very far away, we can use them to measure distance, right? So we can so we can measure the distance between us and a supernova that's very, very far away from us. So if you think about it in the context of an expanding universe, that's extremely powerful because how many of you have heard this analogy of the ants on a balloon for an expanding universe? Some of you? So you've heard this, right? Think of an expanding universe as 2 ants sitting on a balloon, and as the balloon expands, the distance between the ants gets bigger and bigger and bigger, right? So it's not moving with respect to one another. The same thing with galaxies in the universe. The space itself is expanding, so the distance between them is getting bigger. So let's use this balloon metaphor to understand supernova distances. So the first thing to get in your head is that because the balloon is expanding, because the universe is expanding, what does it even mean to talk about the distance between 2 points? Right? I mean, the distance between me and another galaxy, what does that mean? Does it mean the distance now? I just put down an infinitely long ruler? Well, that's one way you could do it. Or you could do it the distance when the thing emitted the light, which could have been billions of years ago. That was a different distance, right? Or is it some intermediate thing? It doesn't make any sense. You have to really be careful to define these things, right? So so understanding the distance clearly will give us some insight into how the universe has been expanding. So this is kind of a technical argument, but let me walk you through it. It doesn't really matter if you don't understand it, but it might be useful to just walk through this argument. So here's the argument. Let's say we observe a supernova. Remember, they're all intrinsically the same brightness, right? Let's say we observe one that appears to us very, very bright. That means it's very close to us, right? So what does that tell us about the expansion history of the universe? What that means is, so let's say you see a supernova, we know it was emitted when the universe was half its size, because we can tell that from its spectrum. So we know that, and we see it's very bright, that means it's close to us. So how could the light from it have gotten to us? Help me out here. So the light from a very close thing got to us as the universe doubled in size. Well, the only way that can happen is if the universe is expanding very rapidly, right? Because if the universe is expanding very rapidly, then light only has a very short time to travel, right? So the time it takes the universe, the balloon, to double in size is really quick. So light can only go a very short distance, right? So if the supernova is very bright, that means the universe was expanding very rapidly in the past. And what that means is the universe is expanding less rapidly today, so that's the definition of deceleration. The expansion is slowing down. Alternatively, if we see very faint supernova, that means they come from us very far away, that means the universe is expanding very, very slowly. So the light had a very long time to travel, right? So it's very far away from us. And that meant the universe was expanding very slowly in the past, and that means the universe today is expanding faster, the universe is accelerating. So you get the idea that by looking at these distant supernova, we can actually tell whether the universe, the expansion of the universe, is slowing up or speeding down, or speeding up. Right? So even if I didn't explain it clearly, you can kind of get the idea, right? It's kind of it's a powerful thing. You can tell us something about the history of the expansion of the universe by observing these distant supernovae. So what's the difference? What does it matter whether the universe is accelerating or decelerating? Well, what should it be? Should the universe be accelerating or decelerating? Well, decelerating. Why? Because you all have the same intuition, right? Here's from a K-12 project from Glenview. The velocity of a rocket versus time. So it goes up, and then it goes down. So the velocity, what happens here? The velocity is going up because it's got fuel. The fuel craps out, and then the velocity starts to go down, right? The object still keeps on going up, right? Because the velocity is still positive. But once you get rid of the fuel, then the velocity starts to decrease. Now, why does the velocity start to decrease? Because the gravity from Earth is causing it to decelerate, right? So once you have you get rid of the opposing force of the fuel, the only force left is gravity, and gravity tends to cause velocities to decrease. It tends to decelerate things, right? So from a high school point of view, you can understand that gravity typically decelerates things, and that property tends to hold in general relativity as well. That if you plot in the context of general relativity what you expect the expansion rate of the universe to do, you expect it to decrease. So this, I guess, is the most technical slide in the talk. So this is what you expect. This is a picture of a plot of what you expect for the expansion rate of the universe to do as a function of what's called the redshift. We live at redshift 0, so earlier times correspond to higher redshifts. So we expect the expansion rate of the universe, if all there is in the universe is protons, neutrons, and dark matter, we expect the universe to be decelerating, the velocity to be, the expansion rate to be decreasing. In fact, the data tell us otherwise. The data tell us that the universe is accelerating. So what that means is there's two possibilities. Either general relativity is wrong, which we don't want to think about that for now. So let's assume general relativity is right. So that means there must be something besides matter in the universe. There must be something, an anti-gravity thing, that's causing acceleration instead of deceleration. And if you think about it, what is it that can possibly cause this? So I've written here something that falls out of general relativity. The expansion rate of the universe is proportional to the square root of the energy density, or the mass density of the universe. So for, what does it matter? Because what do you expect to happen to the mass density of, say, stuff in this room? Well, as the room doubled in size, if you were all locked in here, the density would get diluted, right? Because we'd have the same number of people, same amount of mass, but the volume would get bigger, right? So as the room or the universe expands, we expect the density of matter, of stuff, to decrease with time. And that's precisely the reason why we expect the expansion rate to decrease with time. So if you have normal matter, what you expect is it will get diluted, and that will lead to deceleration. That's exactly what we expect. The only way, in fact, to get something else is somehow, if you have something that as the universe expands, as the room expands, the energy density has to remain constant. It means the total energy has to be increasing. It's really bizarre, right? The same number of people in this room, the room is doubling in size, but the total energy is getting bigger. So it's almost as if the energy is a property of space itself. It's not associated with any individual particles. It's a property of some kind of space itself. So for that reason, we really are at a loss to understand what this stuff is. We just give it a name. We call it dark energy. We know nothing about it, literally. Literally, we know nothing about it. But all we know, the only thing we do know is that it seems to dominate the energy budget of the universe, and it leads to acceleration instead of deceleration. So there are a number of possibilities. One possibility is it can't be a regular particle, but in particle physics we have things called fields. We can add a new field to the standard model of particle physics, and that, however, would require us to make the mass problem much, much, much worse, changing it from a 16 order of magnitude problem to a 50 order of magnitude problem. So this people don't like so much. The other possibility is it actually is a property of space itself. You can calculate the vacuum energy associated with space itself. That's called the cosmological constant. And that, if things worked out right, actually would have the right properties to explain the acceleration. The problem is when very smart people do this calculation, they get an answer which is wrong by the most wrong anyone has ever been. So we really do not understand how this dark energy could be a cosmological constant. I alluded to the possibility that maybe this has to do with the fact that, I drew this curve over here assuming general relativity. Maybe general relativity is wrong. So someone here should come up with a different theory. You have to modify gravity. And then people have played with the idea, coming from string theory, that maybe there are extra dimensions, and this acceleration is some leakage from some extra dimensions. We really don't know, but we're very interested in finding out. The consequences, of course, are cosmic. So let me share with you how this is leaked into the media.
Line here in the New York Times on page 13, and I said to myself, I wonder if this is a page 13 story. Okay. So I brought it in. Take a look at this. Can you read this along with me right there? Astronomers report evidence of dark energy, and they have that in quotes, dark energy splitting the universe. Page 13. Well, that's a huge, that should be on page 1. The universe is the end of everything. What are we going to do when the universe comes apart and they bury it on page 13?
So it's clearly important, right? And we have to try to figure out ways to get at this dark energy because, I plotted the past and we have models for what the dark energy might look like. We parameterize those models, essentially we're parameterizing our ignorance with W, and we, so with different W, different equations of state correspond to different models for what the dark energy is. But of course you can extrapolate in the future and figure out what our cosmic history will look like, and that's important as well. So we really want to be able to distinguish between different models of dark energy. And for those purposes, we here at Fermilab are heading up the Dark Energy Survey. We're involved in the Supernova Acceleration Probe, which hopefully will launch in about a decade or so. And we're thinking about getting involved in the Large Synoptic Survey Telescope, which also will probe properties of the dark energy. So again, a show of hands, how many of you are involved in the Dark Energy Survey, or SNAP?